Hello students. I'm going to go ahead and finish as promised some of those more challenging questions from today's notes. That would include, in my opinion, example 3C. So let's take a look and we'll do some more after this as well. To start with though, example 3C, so we're going to take x plus h and we're going to substitute that into the expression from up above, which if you recall was x squared minus 4x. So when we use substitution of this nature, it is a little bit more interesting because when we do this, x plus h quantity squared and then minus 4 times the quantity x plus h. And if you recall, I might as well write this up above. F of x in the first place was equal to x squared minus 4x. So we're substituting x plus h in for x here and in for x there. Okay, so the algebra will get a little bit tedious here, so let's take a look. X plus h quantity squared, we do need to FOIL, so let's write as such. And then minus, if I distribute the 4, we get minus 4x minus 4h. FOILing first, outside, inside, last, and then still minus 4x minus 4h. Conveniently enough, there's going to be some like terms that unfold. So x squared plus 2xh plus h squared minus 4x minus 4h. It looks quite interesting as a final answer nonetheless, but it is an answer, and that's the answer. I'm going to scroll down here. I think example 4 you should be able to take a look at hopefully and figure out that really mainly as this parameter restricts us to only numbers greater than or equal to 0 and this parameter restricts us to numbers less than 0. You'll pick which function piece appropriately. So for greater than or equal to 0, x plus 1, you'll use for this piece, because it's 2, it's greater than or equal to 0. So you'll pick the first piece. And for this, x is equal to negative 5, which of course is less than 0. So you'll pick only that piece. Moving on. So we did not have the opportunity to talk in depth regarding the 3 specific cases of the domain of a function. So in terms of example 5, and I do expect you to know interval notation by now, it does say though find the domain of each of the following functions, x cubed plus 3x plus 1. This is a cubic, and the question, remember, with regards to what domain entails, the question is, well, what x values or what numbers for x, and really what x values are going to work? Well, we're not limited here. We can plug in a negative number, negative anything technically for x. We can plug in 0, and we can also plug in positive values. So negative infinity to positive infinity is the domain in interval notation. Another way to describe this would be all real. All reals would be perfectly fine as well. Try to get in the habit though of writing it at interval notation as much as you can. For part B, we are limited in this case because x can't equal negative 2. Remember that if your denominator is equal to 0, and negative 2 would put that into that situation, we technically can't divide by 0, so it's not defined. In this case, then you would argue that the domain would be any negative number except negative 2, and then anything beyond that, of course, so negative 2 and beyond to positive infinity. So this particular domain does include everything technically but negative 2. Let's move on to part C. This is an even root. We also refer to it as an even index. And when your index or root is even, you are limited in various ways, as you probably recall. In other words, you can't take the square root of a negative number, at least not in the real number system. Because it's an even index, we like a power, or excuse me, like a root of 2, or a power of a half, I guess you could say. we know that the radicand must always be greater than or equal to 0. And because this is the case, or since this is the case, I'll go ahead and just add x to both sides and flip it around and note that x must be less than or equal to 5. Because this is the case, and again, picking a number to prove that to yourselves, like 5. If you pick 5, it's 0. If you pick 4, it's 1. And so on and so forth. So as long as x is less than or equal to 5, it's going to work. So for this particular problem, the domain in interval notation will look something like this. Remember, we use a parentheses if it is a solution or does work, and we use a bracket, or excuse me, a bracket if it does work, a parentheses if it doesn't work. Okay. This last example, this application problem on this page, the last example, I do believe is a fair one for you to take a look at on the pre-completed notes version. So I'm going to go ahead and take a look with you as the very last example on our screencast here today. Example 7, working with an expression from calculus, specifically something called the difference quotient. So this right here, this difference quotient, is something that is quite regularly referenced in calculus. And because this is a, quote, pre-calculus class, you are going to see some concepts that are prepping you for a lot of the calculus that you will likely see later. So in this particular problem, we've got a function. It says if f of x equals x squared plus x minus 1, it's a quadratic function. It says find what we call the difference quotient. Two things I want to highlight to kick this problem off. This f of x plus h, that is like we saw up in example, I believe it was 3, right? 3c more specifically. Like example 3c, you'll be substituting x plus h into the original f function. And then what you'll do is you'll subtract f of x from it. So that is the second piece. Now I guess the third piece would be the denominator, but that's not as difficult. Literally just writing out or using, I should say, that letter h. You'll understand here in a moment. So what I'm going to do, because the difference quotient looks pretty much as what you see it there, you're going to quite literally take x plus h and substitute it in wherever you see an x. Because again, you are using that input, so to speak, into this f of x function, x squared plus x minus 1. So that in and of itself is your quote-unquote f of x plus h. And from that you'll subtract the original function in f of x form as you see it. So again, this represents in its entirety f of x plus h, and that represents in its entirety just f of x. This whole thing is divided by h. So when we continue, you are going to have to FOIL. And we already did this on example 3, so I'm going to go back and just take what I did there, and I'll say x squared plus 2xh plus h squared plus x plus h minus 1. I will go ahead and distribute the negative to make things a little bit kind of more efficient in the next step. So I'll go ahead and rewrite and then all over h. The beautiful thing that does happen here is that you have some terms that nicely quote-unquote cancel with one another. I did forget a sign. Sorry, this is plus 1 there because a negative of a negative becomes a positive. So some terms actually quite nicely are going to start to unfold, particularly x squared minus x squared. They unfold by canceling, and then negative 1 plus 1. So what we're left with is 2xh plus h squared. Okay, and oh, I forgot to cancel my x's. Those are nicely going to drop out as well, x minus x. All right, moving on. We still have more, of course. H squared and h. All right, we're getting close. As it turns out, you can do a little bit more, particularly with in the numerator there being a common factor of h. Factor out h, and you've got 2x plus h plus 1 all over h. And you may or may not already kind of see that the h's, because they're both 1 in the numerator and the denominator, they cancel such that 2x plus h plus 1 is your end result. The only added nuance to this answer is noting that h couldn't have been 0 from the beginning, and you need to highlight that then at the end as well.